All right, guys, welcome back from spring break. Did anybody not get their midterm? What's your name? Joseph. All right. I think you were the one that didn't put your name on it. I don't think you put your name on it. What's your name? Zach. Zach. Everybody else got it? Oh, awesome. I just want everybody to have them because I'm going to go over it. Autumn. Everybody else has it. Okay, so I guess what I'm going to do is I'm going to allocate like till 3 o'clock to go over this midterm. And then I want to go over capacitors because your guys' next homework is a little bit of review and then some capacitor stuff. So I want to make sure I cover everything. All right, so let me just put my little copy of the midterm here. Were there any, do you guys want me to solve it in order, or do you want, like, are there any particular ones that bothered you? That one. This first one bothered everybody? All right. I hate to do this, but does anyone have a pen I could borrow? Yeah. I don't want to use a Sharpie. All right, cool. All right, so I'll go over this. Everyone can see it pretty good, right? All right, so this one is just like your quiz that I gave earlier in the semester, except there's a voltage source, which it might have tricked some people, but really all that's happening here is, you know, it's a single loop. 1 milliamp is flowing. And so I draw my plus and minuses all around the circuit going like this. And so the first thing I notice is that this is 0 volts, so I can start going this way and figuring out the voltage going around the circuit. So if I have 1 milliamp flowing through a 1K, my drop is going to be 1 volt, right? And so if this is lower than this, then that means that V5 is equal to 1 volt. Now here I have a drop of 0.6, right? I've got 0.6K and 1 milliamp, so this is going to be a drop of 0.6 volts. So going up from 1 by 0.6, V4 is going to be 1.6 volts. And now here I just have a voltage source, right? So I go from, you know, this node to this node. This just tells me I'm going to go up by 2.3 volts. So V3 is going to be 1.6 plus 2.3, or 3.9 volts. Okay, and now you notice I'm still going up. I'm going from lower potential to higher potential. This is a drop of 4 volts, right? 1 milliamp times 4K. So I go from 3.9, I could say V2 is 7.9, and then another drop of 2 volts, so V1 is equal to 9.9. Any questions there? All right. Superposition. All right. If you guys are coming in, here, I'll just put the exams over here so that you can grab them and not walk in front of the screen. All right, so this is just a typical superposition problem. I guess for me, I would, you know, just kind of split my paper into 2 so that I can solve it. I'm trying to find Vx, right? So I know Vx is going to be equal to Vx1 plus Vx2 because I have 2 sources. So the first case would be with no current source, I guess. And then the second case would be with no voltage source. Alright, so with no current source, this circuit's going to look like this. So 3K, 6K, 2K. the 2K is not going to do anything, right? Because I'm not going to get any current flowing through there. So all I end up with is a little voltage divider here. That's going to be my VX1. So I can say VX1 is going to be equal to 6 volts times 6K over 9K, or 2/3 of 6, which is 4 volts. Any problems with that? Alright, and then with no voltage source, here I have a, make sure. Yeah, alright, good. I've got like a solutions manual that I already solved. I just want to make sure I don't do anything stupid. Alright, so now I'm going to short my battery, and I'll end up with this other circuit. Right, 3 milliamps, 2K, this is VX2. Does everybody agree that 3K and 6K are in parallel? Alright, so I need to figure out what that is. Should be 2K. Is it 2K? Alright, so then I could redraw this circuit like this. Or that's 2K, and this is 2K. And I've got 3 milliamps flowing here. So I could say that this is 6 volts, right? 3 milliamps times 2K gives me 6 volts. Alright, so my VX2, that's VX2, is 6 volts. Alright, so then I've got VX1, I've got VX2, which means that VX is equal to 10 volts. And then it says to determine the current through R1, right? The current through R1 is just going to be this current right here. A lot of people made the mistake of overcomplicating this. Guys, all it is I have a voltage of 10 volts here, and I have a voltage of 0 volts here. So my current I is 10 minus 0 over 6K. You don't have to worry about KCL. KCL is happening, but you don't have to think about it, because if I have the voltage here and the voltage here, and I have the resistance, it's just Ohm's law. So in this case, what would that be, like 1.667 milliamps or something like that? Alright, so that's the problem on superposition. Any questions about that? Yeah.
So, for the number 1, you know the 2K resistor?
For this one?
Yeah.
Yeah.
So, like, why don't you combine it with the 6K?
Because, so in this circuit, right, I'm going to have current right here, and then it's going to split this way, and it would split that way, but no current can flow here because there's an open circuit. So this 2K and the 6K aren't in parallel because they're not sharing two nodes. They basically have to share two nodes. Well, this node is disconnected, so this part and this, if there was a wire here, then they'd be in parallel. But because it's open, they're not connected, so they're not in parallel, and you basically only have a single loop.
So when there's no current and the resistor's like...
It may as well not be there.
Okay.
Yeah, because if there's no current here, then the voltage drop across this resistor is 0, so then this is basically like ground. So it's basically, and I drew this wire, but that's not there. Yeah, so if there's no current flowing through it, you can basically disregard it. Alright? Okay. Alright, so that's that one. Try and get through this quick. I might not do all the algebra here. Basically, this is just a typical mesh, and I want you to find the voltages. So I guess if this was me doing this, I would draw one current this way. I'll draw this one this way just because the battery's going that way. And then same with this. People might have defined their currents differently. That's okay. Draw my plus minuses. Up here it's this way and that way. Alright, so if I'm going to make my three equations here, my first one, I would draw from my current source, right? I would just say, okay, I1 is 1.5 milliamps, right? Does anybody still have a problem with this? We're good with that? I can just note that I1 is going to be the same current as whatever this current source is, okay? My second loop would be I2, so I'll go, starting across the voltage source, I would say plus 3 volts minus I2 times 2K minus, and then over here I've got I2 minus I1, note, times 8K. Alright, so that's my second equation. Any problems with that equation? And then my third equation is going to be, I'll also start at the voltage source and go across it, so I'll say plus 3 volts, and then I'm going across this 2K, so that's going to be minus I3 times 2K, and then I go across, this, and I've got I3 and I1 both flowing through this 3K, so I'm going to, and they're in the same direction, so I'm going to add them. Alright, so those are my 3 equations. And now from here, you can plug I1 in right here, and you can plug I1 in right there, right? And if I plug that 1.5 milliamps in, you notice this equation is literally just in terms of I2 now. And so you can just solve for I2 straight up. And then this equation is just in terms of I3, so you can solve for I3 straight up. You don't even have to do any crazy algebra in this one. I set it up that way by putting a voltage source that was shared between these two loops. It makes the algebra much easier. But I don't want to do the algebra, so I'm just going to write, because I already solved it, that I2 is 1.5 milliamps after you solve this equation. And then I3 is going to be negative 0.3 milliamps, okay? And now I'll solve for the voltages using these currents. So what you might notice is that I1 is 1.5 milliamps flowing down here, and I2 is 1.5 milliamps flowing up here, right? That's going to mean that the total current flowing through this 8K is going to be 0, okay? So if I have 0 current flowing through this resistor, and I know this is ground, and that's 0 volts, then this is also going to be 0 volts. So I know some people asked me, like, they thought they did it wrong because they got Vx equals 0, but that's correct. Alright? So now I've got 0. I know I can find Vy because I just have a voltage source here, right, of 3 volts. I'm going up by 3, so my Vy is just going to be 3 volts. Okay? And so now the last one I have to solve for is this voltage, Vz. Well, I know I1 and I know I3, right? I1 and I3 both flow through this 3K. So this Vz is going to be equal to I1 plus I3 times 3K, or basically 1.5 milliamps minus 0.3 milliamps times 3K, which gives me 1.2 milliamps times 3K, and that's going to give me 3.6 volts. So now I got my voltages. Any questions about anything I did there? This is going to take some time. Maybe I'll come back to this one. If we have time, I'll come back to this one. Otherwise, I'll make a video about it. I don't want to run out of time. This one, problem 5. Okay, so this one is just literally, I gave you guys a hint basically. I said note, right? Note that you can reduce the resistance between Vs and Vout down to a single equivalent resistor, so I hope everybody noticed that. Basically, the resistance between this point and this point, this can all be reduced using series and parallel equivalents to one equivalent resistor, right? And then if you do that, it's just a voltage divider, okay? So hopefully you first noticed that the 12Ks were in parallel. So I could redraw that little network there, 3K, 7K. And now if I have these two in parallel, 12K and 12K, you should know by now that if I have two parallel resistors, right, that have the same value, the equivalent is just half. So this will become 6K. You can also do that with the equation. It'll work the same. Right, so that's my network now. And now my 3K and my 7K are pretty obviously in series. And then my 1K, 6K, and 3K are pretty obviously in series. So I can replace this with 1 plus 6 plus 3 is 10, so this is 10K, and then 3 plus 7 is also 10K, right? So this is my VS and my V out, basically. I'm just leaving some of the circuit out. And so now I'm left with a 10K in parallel with a 10K, and that's going to give me 5K, right? So now I know that my resistance between VS and V out is just 5K, so I can draw the rest of my circuit. And what did I ask you for? V out. So V out is going to be half, right? With the voltage divider with the same resistances, I get V out is equal to 5 volts. And then I asked you for the current through R7, which is this resistor. 5 volts minus 0 volts over 5K gives me 1 milliamp. Any questions about this one? All right, now this last one. All right, so this one was not too different from your homework, the last homework I gave you. Although maybe it tricked some people up. So basically, in this little loop right here, we've got 1 milliamp flowing, right? So I know that I've got plus minus, plus minus, plus minus, and it's just 1 milliamp. So right off the bat, I know this is 0 volts, and I've got a 1 volt drop across R5, which makes Vx equal to 1 volt. So let me just write this over here. We've got Vs, Vw, Vx, Vy, and Vz. So I just found Vx, right? That's 1 volt. Now I've got a 2 volt drop across this 2K, right? So 1 plus 2 gives me 3 here. So my VW is 3 volts, right? And now I've got a 3 volt drop across this R2. And so 3 going up by 3, Vs is 6. All right, so that's just this left side of the circuit. I've got those taken care of, and now I have the dependent part of the circuit. And so this current source, right, it's a voltage dependent current source or voltage controlled current source. I've got 3 volts on the plus terminal and 1 volt on the minus terminal. And so what it's reading in is that difference, right? So that is going to read in 2 volts, right, a difference of 2 volts. And then I multiply by 1 milli, basically, so I get a current flowing through here of 2 milliamps. All right? And so now I know this is 0 volts. I go plus to minus a drop of 2 volts. So Vy is going to be negative 2 volts, right? I'll write that here. And then lastly, I need Vz. 2 milliamps flowing there. I get a drop of 2 volts, so Vz should just be positive 2 volts. So now I've got all my voltages. And then I asked, do R4 and R5 dissipate the same amount of power? So let's look at R5 first. The power dissipated by R5 is going to be the current through R5, right? 1 milliamp times the voltage across it, which is 1 volt. Okay? The power dissipated by R4, right, is going to be the current through it, which is 2 milliamps, times the voltage across it, which is 2 volts. Okay? 4 milliwatts. So therefore, no, they don't dissipate the same power. All right? Everybody cool with that one? Any questions? Yeah.
How did you get the current on the right side?
So this source right here, it's called a voltage controlled current source, VCCS. So this value right here is the gain. It's telling me that I'm going to take in some voltage, I'm going to multiply by that gain, and then that is going to act like a current source, okay, so whatever that delta V is in, multiplied by the gain, is going to give me my current through this source. That's how this source works. So the voltage difference in was 2 volts, and the gain was 1 milli, basically. So it's not really, it doesn't care about the unit of volts, it just cares about the value. So it's going to be 2 times 1 milli, which gives me 2 milliamps. It's this 3 volts up here, VW, minus this 1 volt, VX. It takes in the difference between the 2 points. So the source looks like this, right? It's got a plus and a minus, and it's a current source. And so it's taking this voltage minus that voltage and then multiplying it by 10 to the minus 3, basically. So 3 minus 1 gives me 2, right? And then times 1 times 10 to the minus 3 gives me 2 milli. So this is from homework 9. If this doesn't make sense, review homework 9. And we can talk in my office if you need to. Alright, so I've got about 8 more minutes. I guess I could do this one real quick. Does anybody have problems with this one? Alright, so this one, initially you have to solve for Vx, right? Determine Vx is the first thing I asked. So what I would do is just do a quick little mesh where this is going to be I1 and this is going to be I2. And I'm going to say I1 is equal to 1 milliamp, right? That'll be my first equation. And then my second equation is going to be plus 12 volts minus I2 times 6K. And then I've got I1 and I2 both flowing through the 4K. Let me just plug it in because I don't feel like doing extra steps. 1 milliamp plus I2 times 4K. And that's going to give me 0, right? If I solve this out, I'm not going to do it. I2 will give me 0.8 milliamps. Okay, so now I've got my 2 currents. And I can find Vx very easily because Vx is going to be equal to I1 plus I2 times 4K. Right? So in this case it's going to be 1.8 milliamps times 4K, which gives me 7.2 volts. Alright? Any problems with that? Finding Vx? Alright, so now I split my page into 2 for Thevenin and Norton. For my Thevenin circuit, I'm going to draw, without the load. My load is going to be gone. Ground is here, 12 volts, 6K, 1.5K, 1.5K, and 1 milliamp. And then right here is what I'm looking for, right? My Thevenin voltage. Alright, so this is a single loop. I've got 1 milliamp flowing through this 6K, which means I have a drop right here of 6 volts. This voltage is obviously 12 volts because it's just a battery, connected to ground. And so if I go 12 plus 6, I get 18 volts right here, and that's my V Thevenin. Good with that? V Thevenin? Alright, now if I wanted to find R Thevenin, I need to open up sources that are current sources and short out, voltage sources. So if I were to do that, I'll just say V Thevenin here. This would be R Thevenin. I've got a resistor, my load. This is going to be open. And then I've got a 6K and a short. So right off the bat, you should notice that no current will flow in this part of the circuit because this is open. So all of it has to flow through that 6K, right? So that R Thevenin is going to be 6K. And then if I were to draw my little equivalent circuit, it would just be an 18 volt source with a 6K. And then my load, what's my load? 4K. And so if you do that voltage divider, you should get 7.2 volts right there. So that's my Thevenin equivalent. And then Norton, right? I'm not going to solve it other than by just doing V over R. It's going to be 18 volts over 6K, which is going to give me 3 milliamps. So my Norton current is 3 milliamps. I know my Thevenin resistance is the same as my Norton, and then my load is 4K, and if you solve this, you should get 7.2 volts up here as well. Any problems with that? All right, time to start some new stuff. I will scan my neater, nicer solution that I took more time on into, I guess I'll put it online on the webpage in case people are curious and want to use it to study in the future.
Actually, one last question about number 4 that we just did.
Yeah.
The directions that you verified your equivalent circuits are correct by connecting a load resistor and basically doing that. The thing basically I'm asking is that, like, in the future, I only noticed the check marks next to, like, the solutions that I found, and not for, like, verifying the solutions or anything like that. Would we need dot points if we can show, like, our actual work in, like, reconnecting the load resistors?
Yeah, because I want you to show it, but when I was looking for it, I just assumed that you did it right, probably. If you got V7 and R7 and I Norton correct, I probably just assumed that you knew what you were doing. And I saw them. I noted if you did the equivalence. I probably just didn't put a check next to it. Yeah. All right. Time to talk about some new stuff. So how many people here have heard of a capacitor? All right. That's pretty good. So the second half of this class, we're going to talk about, well, we've already used resistors. We're going to keep using resistors, but now we're going to be using some other components. And the first I'm going to introduce you to is the capacitor. You may or may not have seen them in physics. I'm sure you have. In this class, we're not going to be doing anything crazy with them. But basically, for those of you who don't know what a capacitor is, it's a type of component that stores electrical energy in the form of an electric field. All right, and capacitors look like this. There's actually a couple different ways you might see them. The main way that you'll see it is like this. And so you've got, your two leads, and then this is the component itself. Sometimes you'll see them like this, where the bottom plate. So this is So here's the thing. You notice resistors don't matter. There's no polarity for a resistor. We call this polarity when there is actually a side of the component that you need to connect to the higher voltage and a side of the component that you need to connect to the lower voltage. If you connect a polarized capacitor backwards, you can cause some big issues. So you don't want to do that. There are different materials inside there, and if the electric field goes the wrong way, some things can go south, and we've blown up plenty of capacitors. It's not fun. It can be dangerous. But some capacitors are not polarized. You'll typically see this frowning little face looking thing for the polarized capacitor, and if it's not polarized, or it doesn't matter whether or not it's polarized, then you'll see the two flat lines. So we'll go over to Spice real quick and just show you guys what some of those look like. So if I just type cap, you get a capacitor. You can also just hit C. You don't even need to go to that menu. If you just hit the C button on the keyboard, you'll get a capacitor. That's the same with R for resistors. I don't know if voltage sources. Yeah, V for voltage sources. But if you come into the window here, I think there's a polarized capacitor also in here. It might be called pole cap or something. Yeah. Yeah, see, this is a polarized capacitor. So you get the little frowny face on the minus side of the capacitor. Most of the time it doesn't matter. In most applications I've seen, we're not going to use a polarized capacitor. But when you guys take the 221 lab, you're going to be working with what's called an electrolytic capacitors. So I just want to, this is all just a little overview of capacitors. They look like this. They are polarized. So you'll see there's two legs on the capacitor, and one has this like stripe of white with minus signs. That is the frowny face side of the capacitor. There are other types of capacitors that aren't electrolytic, like this one right here. This is a ceramic capacitor. There's no polarity there. You can see it's just, there's different types of capacitors.
It's $71.91.
That's probably like a real, it might be like, let's see, this is probably like a really high voltage rating capacitor or something. Yeah, this one's rated for, this isn't even a capacitor. It's a varistor. I think that's a variable. Yeah, but they don't usually call them that. They usually call them potentiometers. Oh, well, this one can handle 6,500 amps of current. So there you go. That's an insane amount of current. So that's why it's so expensive. I don't know. Well, power systems. Like the grid handles that much current. So different types of capacitors. Here's like a little graphic, I guess.
I think that he's great is holding on to one of those tiny things.
So you can see these aren't polarized. There's nothing telling you that there's a plus side and a minus side. These are ceramic capacitors are not polarized. There's all different kinds. I think in the labs that you'll take here, you'll only see ceramic capacitors and electrolytic capacitors. So just keep in mind that when you do use an electrolytic capacitor, you need to note which side the higher voltage should be connected to. Okay, so that's just a little overview. Now I'll talk a little bit more about them and what they are and how they work. So what a capacitor really is it's basically two conductive plates. That's why it looks like this. So what you're looking at when you see a capacitor is you have like a plate here, and then you might have another plate over here. I'm trying to draw this in 3D. Does that look 3D enough?
Oh, yeah.
All right, so you've got two plates basically, and the plates are conductive, and then in between the plates you've got some material that's not conductive, and that material that's in between is called the dielectric. And so the reason for the dielectric is to keep the two plates from shorting together, because if they short together then you have no electric field. A capacitor basically builds up charge, right? It builds up charge. Let me just draw like a little battery here. I'll draw a little circuit. So if this was a capacitor, that middle part is called the dielectric, and then these are called the plates. And so not all capacitors are made this way, but this is like the standard. So this would be known as a parallel plate capacitor. All right. So let me draw a little circuit here. When I draw them in actual circuits, we're going to be using this component, but I'm just doing this as like an overview. So let me put like a little switch here, and then I'll draw a battery. And we can call this ground. All right. So basically, I've got my little circuit here with a voltage source and a capacitor. And what happens when I close the switch? So in steady state, before the switch is closed, nothing happens. The capacitor is not charged. It's also known as discharged. Okay? It will have no voltage across it. And what happens is when I close this switch, now the capacitor is going to match the electric field or the electric potential of the battery by charging up to that same voltage, and it won't. The system will continue to pour. Okay, so I've talked about this in the past. We know that current flows this way, right? It's going to flow from positive to negative. But what's actually happening is electrons are flowing out of the battery, and they're getting stored up on this plate of the capacitor. Okay, so electrons start coming out of the battery, and they start pooling up on this plate of the capacitor, right? Well, these electrons attract positive charges to this plate of the capacitor, and so that will continue to happen until the potential of this capacitor matches whatever Vs is. Okay, so if I were to redraw this circuit after the switch is closed, I would draw it like this, and let's say Vs was equal to 5 volts, and then this is my capacitor, right? So after I close the switch, you can think of either electrons pooling up on this plate, or you can think of current, filling up the capacitor. a lot of people like to think of capacitors as like a bucket for charge. You're basically pouring charge into the bucket. I know Dr. Baker gives a lot of water analogies in his classes. I haven't done that much this semester, so I'm not going to start now. Not for any particular reason, but I don't want to just throw you guys into the fire with water analogies now.
Throw us into the fire with water now.
Well, that's true. So basically this capacitor will charge up until the voltage across it is 5 volts. Okay? And so there's a couple of important things going on here. The capacitor voltage, so there's an equation for capacitors. It's C times V is equal to Q. And that equation right there is going to be very important on your homework. And basically what it states is that the voltage across the capacitor, that's V, so that's the voltage across the capacitor, multiplied by the capacitance, okay, so you know ohms are the unit for resistors, right, and that's the resistance of the resistor. Capacitors use a unit called farads, named after Michael Faraday. I think he was a big physicist back when this stuff was being discovered. So C is capacitance of the capacitor. That's how we rate capacitors. So you'll see when I go back to SPICE, when I put down a capacitor, right, it's asking for some capacitance, okay? C, that's the capacitance. And what it basically tells us is how much charge can this capacitor store, okay? And so then Q is the charge that is stored. All right? So let's say, and typically values of, you guys have noticed probably that values of resistors and resistances are pretty large values, right? We get like hundreds of ohms, hundreds of kiloohms, tens of kiloohms. Capacitors have very small values of farads. So a big capacitor in an electronic circuit might be like a 10 microfarad capacitor, like very, very, very small in terms of, you know, the unit, right? An ohm is like a very small resistance, but a farad is a gigantic capacitance. So just keep that in mind. So if I wanted to give this, capacitor a value, I might say something like 2 microfarads is the capacitor, and then I might ask how much charge is stored on this capacitor, and I can find that by multiplying the capacitance times the voltage across it, right? So Q for that particular capacitor would be equal to 2 microfarads times 5 volts. And if I take farads times volts, I get coulombs, which is the unit of charge, right? So my Q in this case would be 2 times 5 microcoulombs, or 10 microcoulombs. All right? So just as an example. Before I go any further, are there any questions about anything I've covered? I'm sure there are. No? Yeah?
Yeah, and capacitor. And the diagram. I don't understand why there has to be space. And early in the video as well, that guy was like, he was decreasing the space, and I wasn't able to understand what's the significance of space.
Yeah, that's a good question. So first of all, in the video, he wasn't making a capacitor, he was making spark gaps, okay? And in that circuit, he had high voltage, but in order to get it to actually arc, you need a particular distance, because what happens when you get an arc, right, an electrical arc in real life, is you might have a really high voltage here and a really low voltage here, and the air around the two nodes becomes ionized, but that ionized air will only reach so far. It has like a field around it. And so he had to bring the spark gaps closer together so that they would touch and actually spark. But that's not a capacitor. But your question still matters for a capacitor. So I just gave you guys this arbitrary capacitance, right? 2 microfarads. Well, the capacitance of a capacitor is dependent on the distance between these two plates, okay? So the capacitance of a parallel plate capacitor, let me just draw it in red, it's equal to epsilon, I'll just explain what epsilon is, I'm not going to explain it yet, times the area of overlap of the two plates, okay? So these two plates both have an area, right? They're going to have an area. Whatever that overlapping area is, that's the A in this equation. And then this entire thing gets divided by the distance between the two plates, okay? So this right here would be my distance d. Okay? And then epsilon, this is also known as permittivity. You may have heard it before. Permittivity. So there's permittivity of free space, there's permittivity of different materials. That dielectric could be any number of materials. So when you look up different capacitors, you'll see different materials that they're made out of, or their dielectrics are made out of. What permittivity is it's telling you how capable is this material of permitting an electric field. That's all it is. We don't really have to worry about it. We're not going to be doing anything crazy with it. We're also not even going to really be using this formula. I'm just going to be giving you capacitors, and we're going to be solving for different things using capacitors. But I want you to know that the capacitance of a capacitor is dependent on the overlap area of the plates and the distance between the plates, and then the permittivity of the material in between the plates. Those three things. Okay? I don't know how many of you guys watched the video I sent you guys about the capacitor. I sent it in the group. You guys are lame. Lame. Where was it? Here? No. Here. Okay, so I said I recommend watching this video before coming to class on Monday. But I mean, it doesn't matter. I'm not quizzing you guys on anything today. But this is another electro boom video about capacitors. He makes his own high voltage capacitor. He makes the plates. He minimizes the distance between them, right? He maximizes the area, minimizes the distance to get this huge capacitor that can, store a bunch of charge. So if you guys want to watch it, I think that's a really good video. It's not required, but it's very educational. Let me get back to the video camera. All right, cool. All right, so before I keep going, any questions? Yeah.
If you actually store a charge, if you didn't have it grounded like that, you could just static electricity charge a capacitor.
That's right. Yeah. Yeah. So all that's happening with a capacitor is basically you got these two plates, right? And if you start building up negative charge on one of the plates, it will attract positive charge to the other plate, and then you get an electric field there. And so it stores energy in the form of the electric field. And yeah, one thing that's interesting about a capacitor, right? If I charge this capacitor up to like I said, 10 microcoulombs, and then I disconnect the battery, that capacitor will stay charged. Okay, that's what happened when he got shocked in the video. I don't know how many of you guys saw him get shocked. He didn't discharge the capacitor before he tried to touch it, so it discharged into him. Basically, it's trying to discharge, but if it's not connected anywhere, it won't discharge. It'll stay charged. And so we're going to talk about RC circuits later in the maybe next class or the class after that. But basically, an RC circuit is how capacitors are typically charged and typically discharged. Yeah.
This might be a dumb question, but so whenever you touch the door handle and it shocks you, are you the capacitor and then your body is trying to discharge it, or is the door handle capacitor trying to discharge to you?
No, it's more or less just you and the door are charged electrically to two different potentials, and everything wants to be neutral. So when you touch it, they neutralize.
I didn't know if it was similar to that.
Yeah, like when you rub a balloon on your hair, it builds up electrical charge on the balloon. And so since the negative charges left your hair and went onto the balloon, they left positive charges on your hair, and so then they attract, and that's why your hair stands up.
Okay.
Yeah.
Another question. So when he grabbed the two ends of the circuit, the ground and power, his body essentially function as a circuit itself?
It basically functions as a resistor. So the current will flow through its body. So that's why he said never grab the circuit with two hands, right? If you're going to grab it with one, because then it doesn't have a path to flow through. Well, and another thing you have to make sure of is that a lot of people, we talk about water. You can get shocked because if there's electricity in the water. The reason why that can happen is because water's not a great conductor, but it will conduct if you're touching it. It will conduct, through whatever other parts of you is wet. But in that case, if you touch a really high voltage and a really low voltage, like if you touch, you just put your hand across a 9-volt battery, your body creates such a huge resistance that the current flowing through your body will be so minimal that you won't really feel it. But if it's thousands of volts and your body is still that same fixed resistance, this huge voltage over your body's resistance will create some significant current, and you can get hurt pretty badly. Yeah.
Half-life to capacitors, where they'll lose charge
Okay, so that's called leakage, and it also depends on where they're connected. So if you just charge a capacitor and then you just set it aside somewhere and it's not connected to anything, theoretically it shouldn't lose its charge. It will stay charged until somebody touches it or something touches it. But in systems, like on an integrated circuit or on a circuit board, everything's connected to something, right? The capacitor might be disconnected electrically, but it's still connected to the circuit board, so you'll get some leakage into the circuit board. And it happens in memory too. So DRAM is a type of memory, dynamic random access memory. It uses basically a little switch and a capacitor to store ones and zeros. The capacitor being charged will hold a 1 in binary, and the capacitor being discharged holds a 0, right? But they have to continuously refresh the capacitor every so often because of the leakage, right? So if there's a 1 in there, after some time, it will just lose all of its charge, exactly like you're saying. So they have to refresh the circuit and keep rewriting that value back into the cell, otherwise it won't store its charge. And so that's how RAM works, or DRAM at least. There's different types of RAM. But flash memory doesn't use capacitors. Flash memory uses something different, and that's like why you can carry your flash drive around and it never loses its data. Basically, for tens of years, like decades, you can carry a flash drive around and you'll have the same memory on it because it's not stored in capacitors. It's stored in a completely different way. If you guys are interested, I can elaborate.
Yes.
Yeah.
So basically, I've talked about MOSFETs in the past. This is like a little tangent. Don't give me more than like 2 minutes to go on this tangent. So a MOSFET, right? It's basically a switch. Current wants to flow through here, and it can only flow through here if the voltage between these 2 points is high enough. And that voltage, that high enough, is called the threshold voltage, okay? And so that threshold voltage is dependent on a number of factors. At the atomic level, what you have is this is called the gate, this is called the drain, and this is called the source. So if I were to draw this in 3D, what you're actually looking at on a chip, so this is like, I'm drawing this in 3 dimensions, guys. I'm trying to. So now we're looking at like a cross-section of a transistor here. I've got my gate here, I've got my drain here, and I've got my source here. So electrons want to flow under this gate, all right? So there's a bunch of electrons just sitting around down here in this, what's called the substrate. And when I apply a voltage, a positive voltage to the gate, that's what I have over here, right? These electrons get pulled up underneath the surface of that gate. And now I have a channel of electrons between the drain and the source. And now current can flow from the drain to the source because I didn't have electrons there prior, free electrons. Okay? Well, what they do in flash memory is they'll put a gigantic voltage on this gate. So large that these electrons don't just get pulled under the gate, they actually get yanked through the silicon into the gate. And now you have electrons sitting here that repel electrons. Okay? Because electrons repel each other. They're the same charge. And now, since there's electrons sitting on this gate that will repel other electrons, the threshold voltage is larger. And so they actually manipulate the threshold voltages of these devices. And a higher threshold voltage would be a 1, and a lower threshold voltage would be a 0. And so that's how flash memory works. That's why it's non-volatile. And you don't need power to keep it, because it's actually physically manipulating the structure of the devices. It's not just stored charge.
I think the best way I can think of this myself is like, it's like magnetic water. It's like the gate's pulling the water up, and there's kind of like be a stream there. If it pulls too hard, it kind of pulls the stream through the gate, and then it just has like a body of water here, then just a stream of here that doesn't touch.
Yeah, that's right. I mean, that's literally what's happening. You basically have all these electrons sitting down here, and the material's neutral, but when you put a voltage at this gate, electrons get pulled up into this region here, and now you have a channel of electrons where current can flow, right? And so if anyone's more interested in that, you can go to my webpage, and I have a flash memory presentation that I gave. If you go to my projects, let's see. Presentations, multi-level flash memory research. If you click on this, I did like a little PowerPoint presentation on flash memory, talk about all this stuff. So it's really interesting if you guys are interested. Yeah, what's your question?
It seems
If it's really not simple, we might not have time for it.
Yeah, if it's not simple, I'll just come back to so or something. But so a positively charged thing is just the removal of electrons. So when you say you're putting a positive charge there, are you like forcing electrons? Like, are you pulling the electrons from there, and the electrons are moving up?
So what would it?
Like a positron that's being put in.
So what's happening is it's the absence of electrons, right? So when I draw these pluses here, I'm saying these negative charges are flowing here, right?
Right.
Well, they're coming from here.
Right.
So if I took 4 electrons off of this plate and I added them to this plate, they were originally neutral. But now the absence of these 4 electrons is 4 positive charges on this side, and the presence of those extra 4 electrons is a negative charge on this side. So now you have a charge difference,
Okay.
right? Does that make sense? They're basically getting pulled through the source.
Yeah, that makes sense. I will follow up question, but I'll ask that later.
What was that? You have a follow-up question?
But I'll ask that later.
If it's related, you can ask
I mean,
it.
okay. Well, the thing is, like, what is the difference when it comes to data then? Is an electron just an electron, or is there like a difference in it? So if you remove 4 electrons and then those 4 electrons get replaced by 4 new electrons, how does that change the data in and of itself?
Well, the data is read. Capacitors are used to read if the capacitor is charged to some particular voltage. We will measure that voltage, and then we can note. It's much more complicated, right? DRAM is much more complicated than just. There's a way that we read whether or not that capacitor was charged or discharged, and we're going to talk about that next time. Actually, one of your homeworks talks about it. It's called charge sharing.
Uh-huh.
So if I have 2 capacitors that are charged to 2 different voltages,
Right.
and they're not connected to each other, and then I connect them.
Right.
Their charge will share, so that the entire system now is sharing the charge between the 2 capacitors. And there's a little, I think there's a homework problem on it. It's really simple. It's actually really interesting, and it's really useful in memory.
They work opposite of resistors. In
Cap-
terms of like in series and parallel, they work opposite of resistors in terms of their equivalent capacitance.
Yeah, so that's something else I need to talk about today. I think I still have plenty of time, right? I'm not giving a quiz, so I still have like 20 minutes. Let's see what we got for homeworks. So I posted the next 2 homeworks. The one that's due next time is real simple. So these are just, typical using voltage-controlled current source here and a current-controlled voltage source. It's just, 2 more circuits on dependence. Nothing crazy. And then down here you have to use the CV equals Q equation. And then down here I'm talking about parallel capacitors. So this is something I need to talk about right now. So let's go into that. So far I've talked about CV equals Q. I've talked about the capacitance equation. Let's talk about this a little bit further. So obviously what this means is that if I increase the area of the plates, right, the area of overlap, then my capacitance increases, right? Are we all familiar with proportionality, right? This C and this A are proportional. So if the area goes up, then my capacitance goes up, right? And that's basically because I can store more charge on the plates, right? If they're bigger, it's intuitive. Now the distance, I didn't used to think was intuitive, but I did some research and now it makes sense. So if the distance goes down, right, my capacitance goes up, right? And that's because now the 2 plates are closer together, so the electric field is stronger. If they're further apart, then I'm making that electric field. You guys are familiar with the gravitation, equation where if the gravitational force between 2 objects increases if their distance decreases. It's that same exact principle with charges. Basically, Coulomb's law is basically that the electric field between 2 objects is, proportional to the 2 charges multiplied by each other divided by the distance between them. If you increase that distance, the electric field increases.
But the electrical constant is a lot stronger than the gravitational constant.
Exactly. Yeah. So the Coulomb's constant is a lot stronger, like 20 orders of magnitude stronger or something than the gravitational constant. So electric fields, are pretty strong. But I just want to give you guys, an overview of what this. Again, we're not going to be using this. You'll see this in physics if you haven't already. Area goes up, then my capacitance goes up. The distance between the plates goes down, then my capacitance goes up, and then E is just the permittivity of whatever your dielectric is. Okay, so it could be any number of materials, and there's like charts online for these. If you're like, look up what is the permittivity of tantalum, you'll find it, and then you would use that in your equation. But again, we're not doing that. So let me get into parallel capacitors. Just like resistors, capacitors can be added in series and parallel. Although very, very rarely in my entire career have I seen any series resistors, or sorry, series capacitors. They were used in that electro boom video that we were just watching, because he wanted to split the voltage that was dropped across them, just like a voltage divider. But I haven't seen it often, so I'm not going to use it in this class. But exactly like Jaden said, so let me just go capacitors equivalent. It's the opposite of how resistors work, right? So with resistors, right, if I had two resistors in series, I went R1, R2, I could say that my R equivalent was equal to R1 plus R2, right? That's resistors in series, right? And then resistors in parallel my REQ is basically, R1 times R2 over R1 plus R2, or, the 1 over R1 plus 1 over R2, whatever. So this is for series. And then this is for parallel. Alright, so capacitors are the exact opposite, okay? Which is good for you guys, because that means all you have to worry about is adding them. So if I have parallel capacitors now, their equivalent capacitance is equal to C1 plus C2. Right? However many of them I add, right? If I have, all the way up to, I'll just draw dot, 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 and then I'll draw one more here. What's that? Cn. However many of them you put in parallel, you just add them. Okay? And that's really easy, right? And this is the more, the much more common case, because we use capacitors in parallel all the time in all sorts of places. I have, like I said, yet to see an application for series capacitors. But they do operate the same way that resistors operate in parallel. So if I had, two caps in series, then my parallel, or my equivalent, would be C1 times C2 over C1 plus C2. All right. Any questions about that? It's literally the exact opposite. So if you are fine with resistors and you just remember that capacitors are the opposite, then you'll be fine. All right. So any questions about this? All right. So yeah.
I don't quite understand when I look at these diagrams. How are the capacitors opposite to resistors? They kind of look the same.
They're not opposite. I'm saying that when you have capacitors in series and you want to find the equivalent, you have to do the opposite of what you do for a resistor, and vice versa for parallel. So for resistors in series, you add them. For capacitors in parallel, you add them. For resistors in parallel, you use the product over the sum. For capacitors in series, you use the product over the sum, right? So you see this equation and this equation are related, while this equation and this equation are related. Right?
Yeah. Is it because capacitors are usually in parallel?
Capacitors are usually in parallel because typically what you want is, let's say we only have 1 microfarad capacitors and we need a 10 microfarad capacitor. We just put 10 of them in parallel and now we have a 10 microfarad capacitor, right? Based on physics, I don't know why that's the way that they work, but that's just the way that they work. It's basically because you're just connecting all of these plates to each other, right? So if I had, like a parallel plate capacitor, like I said earlier, right, and I connected it to another parallel plate capacitor, sorry, trying my best. guess this would have had to have gone up there. I basically just have double the area here now. Like this is a conductor, this is a conductor, and this is a conductor. So I basically just doubled the area of that plate. So I can just add them. I can add their capacitances. I think that that's probably why they work the way that they do. All they're doing is storing charge. So if I add another one in parallel, I basically just doubled the area. All right. So we just reached 1 hour. This freaks me out every time. I'm like, 1 minute, what? All right, we're good. Okay, so those are capacitor equivalents. So let's look at that homework problem that you guys had. I want to talk about it so that nobody freaks out. All right, so when you have a bunch of capacitors connected in parallel, they typically call that a capacitor bank. And they're used for different purposes. They're always used on the output of circuits for several reasons. But so let me just read this question. So it says a capacitor bank is designed for the output of a 5-volt voltage regulator. So I'm just giving like an application problem. The capacitor bank consists of a 1 nanofarad, 10 nanofarad, 100 nanofarad, and a 1 microfarad capacitor connected in parallel. Everybody sees they're connected in parallel?
Yeah.
What is the equivalent capacitance of the capacitor bank in microfarads, assuming the output voltage is 5 volts? How much charge is stored in the capacitor bank? So if I were to do a problem similar to this, I'm going to do a problem similar without the application. And I think it would be good to spend the next, I have like 12 minutes, working some examples for you guys. And then you should be fine and dandy to do that homework. Let's use brown. All right, so let's say I've got a circuit, some voltage, got a switch, and I've got some capacitors. Another thing we're going to talk about in this section is initial conditions in LT Spice. So in LT Spice, you can set initial conditions on your circuit. And what I mean by initial conditions is let's say I called this node V0 and I call this node VI, or VO, VI, V in, V out. Say this is 5 volts. Let's say this is 1 microfarads and this is 10 microfarads. So if I want to make sure that Spice knows I want these capacitors initially discharged, I can write a statement in Spice to set V out initially to 0, right? But there's also going to be times when I want them to be initially charged because we're going to work on discharging capacitors also. So you will go into Spice and set them to be initially charged. So I haven't done that yet, but I'll do that probably next time because I don't think this next homework does much in Spice. There's no Spice here. These don't have any Spice. And then this is just old stuff. Oh, I did say to verify your work using a transient sim in LT Spice for these power calculations. I know I went over that, but if you want to, just so that I can say I did it again or went over it again, you're going to have to run a transient. So instead of .op, you do .tran for any amount of time because it's DC, so it doesn't matter. And then you alt-click on one of the resistors in Spice, and that will plot the power dissipation of that resistor. You can also plot the voltage across it and multiply that by the current through it, but it's easier to just alt-click. And you know what? Let me just do it real quick. Just one. I'll put a voltage and a resistor, just so you can see what I'm talking about, because this is what you're going to use for that part of the homework. There's no Spice on the rest of it. Let's say this is 5 volts and this is 1K. That would be 5 milliamps times 5 volts, which means this should be 25 milliwatts, right? 5 volts, 5 milliamps. So I do a .tran. I accidentally typed 12, but you just probably use 1. Run it, and then I go here. You can see that if I click this, I get the current. You can't see it, but it's 5 milliamps. The voltage here is 5 volts. And then if I want the power, I alt-click. You see how that little thermometer pops up? So I get 25 milliwatts, like I said. Here, let me just see 25. So that's all you have to do to do an. I asked you specifically to use a transient simulation to get the power and prove that you got the correct power. Each resistor is going to be different, obviously, so you're going to have to basically take them one by one and then add them. So if I were to throw another resistor in here, you could theoretically run the system again, and then you'll see that this one is going to have 6.25 milliwatts. Yeah, and then the same with this one. You can add plot pane and just separate them. And if you just get all of them like this, preferably make sure that you go in Spice and change your background to white so you don't waste a bunch of black ink. I went over that at the beginning. But get a stack of these so that I can see, or Abraham can see 6 milliwatts, 6 milliwatts, and then just add the values, and that's your verification. That's totally fine with me. Okay, what do we got, 10 minutes? All right, so I'm going to do this example. I just was prefacing this with initial conditions because right now the capacitors are initially discharged. So they have 0 volts across them, right? And so when I close this switch, they're going to charge up to where there's 5 volts across them, right? Both of them. They're in parallel. So you have to think of them still as if they were in parallel, the same way we thought of resistors. They share 2 nodes, right? They both share VO and they both share ground. They have the same voltage across them, just like resistors in parallel, right? So that you treat them the same, but if you want to find an equivalent, you have to treat them like series resistors. You have to add them. That's the only thing. Okay? So the question here would be how much charge is stored on the, in the circuit. And so I have some charge stored on the 1 microfarad capacitor, and I have some charge stored on the 10 microfarad capacitor. And so if I wanted to solve that, I would use that CV equals Q equation, right? I know the capacitance and I know the voltage, so I can find the charge stored on each of them, right? So let's call this C1 and we'll call this C2. So I would say maybe Q of C1 is going to be 1 microfarad times 5 volts, 5 microcoulombs. And then I would say Q of C2 is equal to 10 microfarads times 5 volts, or 50 microcoulombs. So then the total charge stored in the circuit would be 55 microcoulombs. Any questions?
You could have just added those charges together and done it that way as well, right? Yeah, sure.
The capacitors?
Yeah, but I know that.
Yeah, so if you wanted to, make an equivalent circuit, you could just go like this. Right? And so then this would be 5 volts. I close the switch, and then I have 5 volts times 11 microfarads. That's my C times V. Oh, they're flipped. V times C. Same thing, right? Okay. Any questions here? All right, so I think that's pretty much it for today. I might go over one more thing, so don't get up. Let me just look at the lectures. So today I said solve the midterm, answer questions, introduce capacitors, discuss charge, voltage, and equivalence. I've done all those things. We just briefly go over energy storage of a capacitor because it's another really quick equation that you're just going to have to memorize. So CV equals Q is one to definitely memorize. I don't think you'll have a hard time memorizing it. The other equation is how much energy is being stored in that capacitor. And that equation is 1/2 CV squared. That's the energy stored by a capacitor, in a capacitor. Okay? So if I ask you how much energy is being stored in this, in one of these capacitors. Let's just say I said how much energy is being stored in the 1 microfarad capacitor. So you would say the energy in C1 is going to be 1/2 1 microfarad 5 volts squared. Note that the V is squared, not the C. It's not CV squared. It's C times V squared. And so that's going to be in terms of joules. So if I wanted to go 5 squared, divided by 2, so 12.5 microjoules. Of energy. All right. So yeah, these two equations right here, this one, that's charge stored, and then this one right here is energy stored. The last thing I'm going to say real quick before I let you guys go, so the next couple classes, I think I wrote it down, we're going to be talking about RC circuits. So RC circuit just means a resistor and a capacitor, right? You may have talked about them in physics already. Basically, when we charge capacitors, we never charge them like this. We never charge them without a resistor because we still want to limit the current. We can damage the capacitors if we don't. Okay? So I omitted resistors here, but in a real circuit, you would have a resistor here, and you would have a resistor here. And that resistor basically limits how fast we can charge or discharge the capacitor. So in these cases, it charges instantly, and we were basically just neglecting the fact that there's some resistance there, and we were assuming that they're already fully charged or they're already fully discharged, and we were neglecting to mention the time and what's going on while they're charging and while they're discharging. So just so you know, for the next couple classes, when I do get into this stuff, we're going to be doing some transient simulations where we actually go over what's happening when they charge and what's happening when they discharge. Yeah.
Because the capacitor's two plates aren't actually touching, and they're just building charges opposite of each other, there is no current flowing through a capacitor, correct?
That's right. So capacitors have what's called displacement current. Basically, if you push, no current will flow. That's something I didn't mention today, and I should say real quick. In a DC circuit, a capacitor acts as an open. It basically acts as an open. So if I put 5 volts here and I put 0 volts there, nothing's going to flow through it.
Yeah, we're not on the camera.
Oh, sorry. If I put 5 volts here, right, and 0 volts there, it's not going to flow like Ohm's law. Like, Ohm's law does not apply to capacitors, so just keep that in mind. Capacitors are open in a DC circuit. But in an AC circuit, you have, waves going back and forth, and the effect of that is that if I have, a high voltage and then a low voltage and a high voltage and a low voltage, it induces something on the other plate of the capacitor that looks similar. And so what you get is what's called a displacement current. Charges that are displaced on this plate are basically displaced on this other plate. So you get current to flow in an AC circuit through a capacitor, but not in a DC circuit. Okay? So yeah, that's pretty much that. Any other questions? All right, guys. We'll see you on Wednesday.